Hi, everybody. This is Miss McClellan here to go over Notes 2.1.1 with you. What information do I need for triangle congruence? So our learning goal is, and we'll write it in the first person, I will be able to identify congruence criteria and that will include certain theorems, and they will be abbreviated as SSS congruence, angle side angle ASA congruence, angle side congruence, hypotenuse leg congruence, side angle side congruence. And that's all of them. And we're going to identify that congruence for triangles. To solve relationships in geometric figures. Period. Okay, 2-1. Recall that if two polygons have the same angle measure and side lengths for all pairs of corresponding angles and sides, then the two polygons are congruent. We're going to verify that all the corresponding side lengths and all the corresponding angle measures of the two triangles are in fact equal. And we're going to do that by starting with some rigid transformations. As a reminder, a sequence of rigid transformations is just moving one figure onto the other with rotation or translation or reflection. So I'm going to move the vertex I onto the vertex N. And then I actually can't rotate with the program I'm using, but hopefully you can see that if I were to rotate this figure, I could make it match up with this triangle. All right, let's define that sequence of rigid transformations. The first step was to translate angle I onto angle N, then rotate clockwise about angle N until angle R and angle A match up. We continue. Write a congruence statement for the two triangles. My congruence statement is going to be T, I mean to write in blue, T, R, I, the first triangle, T, R, I, is congruent to triangle G, A, N. G, A, N. Is there more than one correct congruence statement? Well, absolutely there is. All that really matters is that the corresponding angles are written in the same order. So, for example, as long as angle T and angle G are written in the same sequence, angle R and angle N are written in the same sequence. Oh, I made a mistake. Should R and N be matched up? No. I and N should be matched up. R matches up with A because R and A are the right angles. So I know that there's more than one congruent statement because there are several ways to match the angles correctly. And I'll just give an example of two more. I could do triangle RTI congruent to triangle, and I'd have to use A next because R was first. Triangle A. T matches up with G, so I'd have to write G next. I matches up with N, so I'd have to write I next. Another example, since I said I would do two, triangle, let's see, last time I started with R, first time T, this time I'll start with I. Triangle I, T, R is congruent to triangle. I have to start with N since I started with I. N, I have to start with, the next has to be G since last time I did T, N, G, A. Let's review, just make sure this is super clear, how to write congruent statements. The first thing you want to do is identify the corresponding quarters or vertices. So for example, in this diagram, angle A is congruent to angle D. A and D. Angle B is congruent to angle E. And angle C is congruent to angle F. Step 2, right triangle. The first triangle vertices is congruent to the triangle, the second triangle vertices. The vertex order is critical. It dictates which part of the triangles correspond. Here's an example of a correct order. Triangle ABC is congruent to DEF. If I had written BCA as the first thing, that would be fine. I would just have to say BCA is congruent to EFD. If I started with CAB, I would say triangle CAB is congruent to FDE. It would not be correct to say ABC is congruent to EDF because that would not be listing the angles in corresponding order. A does not correspond to E, so these two wouldn't be matching. Another incorrect order, if I started with triangle BCA, I could not, for example, have the next triangle start with anything other than E. So if I started with F, I already know I'm wrong because B and F do not correspond. If I started with CAB, then I know that it would be wrong to start with anything other than F. So for example, if I had started with D, I would know that would be wrong. Order matters. Next problem, 2-4. In a previous course, we investigated congruent triangles. That was in IM1. We're going to use our graphic organizer from this lesson to review the triangle congruence theorems. And then we're going to come back and do these problems. So the graphic organizer is the last page of the notes. If you see right here, we have it. Please title your graphic organizer Triangle Congruence Theorems. And do you remember what they are? I'm going to name the theorems first. We have side, side, side. That's SSS congruence. We have side, angle, side. That's SAS congruence. We have angle, side, angle, and that is angle, side, angle congruence. we have angle, angle, angle. That's, oops, sorry, I made a mistake. Angle, angle, angle is not a congruence theorem. I should have said angle, angle, side. That's AAS congruence. We have hypotenuse leg. That's HL congruence. And we're going to go over the Pythagorean theorem, even though that's not actually a congruence theorem. And then I'm going to give you a little caution at the bottom. Donkeys. That's what we will call this, ASS. And cars, that would be 3 A's, AAA, don't work. So there's two acronyms that actually can't prove congruence, and those would be ASS and AAA, which hopefully you have a recollection of learning from IM1. Okay, let's go into defining these. Side, side, side congruence. If all three pairs of corresponding sides are congruent, then the triangles are congruent. Here's a quick diagram. Remember your tick marks, everybody. They're super important. This is an example of side, side, side congruence. Next theorem. Side, angle, side. If two sides of the triangles and their included angle which means the angle between the sides are equal in both triangles, then the triangles are congruent. Here's a diagram of that. So we're going to have two triangles with two pairs of congruent side lengths and the angle between them, this between, the included angle, that's a key feature of this one. We have side, angle, side congruence. Our next theorem, angle, side angle. This is like the last one, except instead of having an included angle, you have an included side. So here we go. If two angles of each triangle and their included side, and that's the side between the two angles, are equal, then the triangles are congruent, period. Let's do our diagram. So we've got a congruent side between corresponding congruent angles. That's angle, side, angle, congruence. Next, we'll have angle, angle, side. If two angles and a non included side, so not between the angles, are all equal, then the triangles are congruent. I'll start my diagram. All right, and I'll do my angles. Where do you think I can't put the side length marking? If you said I couldn't put it between the angles, you were correct, because I need a non-included side length. So I'll choose this one. Angle, angle, side, congruence. Now this happens to need to be in sequence. So you'll notice that this angle and this angle are congruent. It would not work to have my congruent side be next to the double ticked angle in one triangle and next to the single ticked angle in another triangle. The side has to be attached to the same angle in both triangles. Next, I have hypotenuse leg. Okay, so for right triangles, and only right triangles have an hypotenuse. So for right triangles, if the hypotenuse and one leg of each triangle are equal, then the triangles are congruent. Okay, let's draw this. These are right triangles having congruent hypotenuses, and one congruent leg. And these are congruent by what we call hypotenuse-leg congruence. Last, the Pythagorean theorem. This just happens to come up a lot in these kinds of problems that we're going to be doing, so we're including it. But I want to emphasize the fact that the Pythagorean theorem is actually not a congruence theorem. So not a congruence theorem. But it is a useful theorem, and we're going to make use of it. Okay. So if a triangle has a right angle, then a squared plus b squared equals c squared, where a and b are leg lengths for the triangle, and c is the length of the hypotenuse. Oopsie. So here we go. A squared plus b squared equals c squared if and only if you have a right triangle with legs a and b and hypotenuse c. So now we're going to do 2-4, trying to determine if these triangles are congruent, and then we're going to use transformations to map one triangle on top of the other, assuming that they are congruent. Here we go. First one, are the triangles congruent? You know, I think it would help if we had a list of our congruence theorems. So I'm going to put them on the side of this page, but you can probably just look at your green sheet, or if it's on white paper, your triangle congruence theorems graphic organizer. We have side, side, side congruence, side, angle, side congruence, angle, side, angle congruence, angle, angle, side congruence, hypotenuse, leg congruence. And then please always remember that donkeys and cars don't work. ASS is not a congruence theorem. Side, side, side is a congruence theorem. I meant to say angle, angle, angle. Angle, angle, angle is also not a congruence theorem. Part A, are the triangles congruent? The information we're given is two sides and an included angle. And it looks like we've got congruence for each of these sides, so, and with the included angle, so yes, they are congruent. A, B, C is congruent to, let's make sure I do these in order. A corresponds to F, because that's touching this side length 8 and is not the 70-degree angle. So ABC is congruent to F, E, D by side, angle, side congruence. And what rigid transformations could I use? Well, I could map angle C to angle D and then rotate. Now, I don't have the ability to rotate with this program, so you're going to have to imagine it, but I would translate angle C to angle D and rotate clockwise until angle B matches with angle E. Next problem. Part B. Are the triangles congruent? Yes or no? Let's see. I have two side lengths which match up. I have 16 and 16 and 12 and 12. And I have an angle. However, for this triangle, the angle is included. And for this triangle, the angle is not included. So in this case, I actually cannot say that the triangles are congruent. So no, they're not necessarily congruent. Oh, sorry, for part A, I should have said that yes, they are. Okay, let's continue. Part C, are the triangles congruent? Here we go. What do we have here? Well, I can see right away that I have vertical angles, and vertical angles are congruent. So I've got an angle. And then I also see that I have these nice parallel lines. And parallel lines are awesome because they give us all sorts of angle pairs. Let's see. I think I'm going to use angle M and angle Z. Angle M and Z are congruent by, let's see, angle M is congruent to angle Z by alternate interior angles, since line NM is parallel to line ZY. All right, let's go. So since I have this, that means I have angle, side, angle, angle, side, angle. I should mark M and Z another time to show that those two are not the same as X. All right, I'm going to go MXN. Triangle MXN is congruent to triangle ZXY by angle, side, angle congruence. And what transformations would I need to do? Let's see if rotation would be enough. Let me think. If we did this, I would just have to rotate. Okay. Rotate triangle MXN about angle, about point X, clockwise until angle N matches with angle Y. If I just rotate this triangle, it'll match up. So those were indeed congruent. Yes. Part D. Are these triangles congruent? Yeah. I gotta say, yeah, they are. I see it. Yes. I've got two right triangles, and they have a matching hypotenuse. And this line right here is the same line for each triangle. So it has to have the same length for each triangle. So let's make our congruent statement. This is going to be by hypotenuse leg, which is only allowed for right triangles. And we have triangle ADC is congruent to triangle ADB. Transformations. For this one, I would have a reflection. So here's my line of symmetry, and I would reflect across. So reflect triangle ADC across line segment AD, and I would land right on top of the other triangle. Here we go, another one. This one's interesting because I don't think it's going to be drawn to scale. So far, I know that the triangles share a side length, and they share an angle, and I have parallel lines. What can these parallel lines tell me? See if I can make that more straight. Let me treat this as a transversal. Okay. I'm hoping to have alternate interior angles or something like that. And I do. So because EF is parallel to HG, and this transversal HF crosses them, I have some congruent angles inside. So I have angle EFH is congruent to angle GHF by alternate interior angles. Which means I have angle, side congruence. So triangle HFE is indeed congruent to triangle FHG. Be careful with your ordering. I'm making sure to order the angles correctly. I have H matching with F, then the other F matching with the other H, and E must go with G. And this is congruent by angle, side congruence. Now, since these triangles are not drawn to scale, I mean, G and E look pretty different, but I'm told they're the same. Anyway, since they're not drawn to scale, the reflection or rotation process is a little bit confusing. So let's think about it. I want F to match up with H. And I want E to match up with G. Okay, I'm going to add another point on this triangle right here, and I'm going to call this A, B, C, D, E, F, G, H, I. And I'm going to say let point I be the midpoint of line segment HF. And the transformation I will use is to rotate about I clockwise until angle E matches with angle G. And that would also bring angle EFH to angle FHG. Last problem. Are the triangles congruent? Yes or no? Let's think about it. I see that we have two sides and an angle. and the sides are in sequence, and then the angle comes next. So we have SSA. And it is tempting to say this doesn't that this works, but it does not. Pardon me. ASS is not a congruence statement. This is a no. And let me show you an example as to why. So check out this triangle. I'm going to draw a line here, like so. And I'm going to have the third edge be here. So here's a triangle, A, B, C. This triangle, I'm going to have it, the lengths be this one and this one. And let's name this angle. This triangle has two named sides and a named angle, but watch. If I let B come right down and swing, it could go to here. And I'll call this C prime. Then I could have triangles ABC and triangle ABC prime. And they would have two side lengths in sequence and a shared angle, but they would not be congruent. Angle side side does not work. It's ambiguous. There are two ways for this second side to land without changing angle BAC. Angle side side does not work.